This video will cover Part 3 of Chapter 1, The Science of Psychology for PSY 110S, the Psychological Sciences. In this section of the chapter, your authors cover the different types of broad categories of statistics that researchers use in order to interpret their findings. Before we kind of look at these broad categories, which includes descriptive and inferential statistics, just remember that when researchers collect data, they have to do more than just look at it and make guesses. We have to use mathematical methods of statistics to help us determine the reliability of those findings and give us basically some rules for whether or not we can be confident that what we're seeing in the numbers, what we're seeing in our data, actually means something. So these broad categories of statistics include what are called descriptive statistics that are used to describe whole groups of people. So if I have a sample made up of individual people, each of them maybe has a score. So for example, if I have a group of college students, they all have a GPA. And so I would have the ability to say what is the average GPA of the freshman class that came into the University of Mount Union in the fall of 2023. So after they finished their first year, what was their average GPA? I could also ask the question, what's the median GPA? What's the most common or the modal GPA? Those are all measures of central tendency. And then there are measures of variability. It's like how widely spread out are their GPAs in that group of people. All of those are statistics that are used to describe the sample, basically telling you where they're at on some variable of interest. Inferential statistics are used in order to test correlational hypotheses or to test experimental hypotheses. So you could have a hypothesis saying that you expect there to be a significant correlation between variables. You could use a statistic to test that. You may also have a hypothesis that argues there's going to be a difference in scores between two groups. And you could use a specific inferential statistic in order to test that expectation. Measures of central tendency are used to give you simple terms to describe an entire group of people with single scores. So with the example that I gave earlier, you could talk about what is the average, the statistical or arithmetic average of GPAs in last year's incoming class of first-year students. You could ask all kinds of questions about populations of incoming students, like what's their median or their mean family income or something like that. The types of measures of central tendency that are typically used in psychological science, the most common by far is the mean or the numerical average, where you take all of the scores, you sum them and divide by the number of people or the number of scores. The median is the score that if you put all of the scores in a group, in a sample, in order from low to high, and then you pick the middle score. That represents a central position of scores within that distribution. The mode is the most common score in a distribution. Now we use these measures in different contexts. Most of the time we're going to use the mean because it's the most commonly used in other kinds of statistical procedures. It also has the advantage of taking into consideration every single score in the distribution, whereas the median only takes into consideration one score and its relative position related to the other scores. And the mode only takes into consideration those most common scores. It doesn't take into consideration anything else, any of the other scores in that distribution. We use the median and the mode in special circumstances that I'll talk about later. Basically, we use the mean if we're fairly confident that scores are predictably distributed throughout the group of participants. We use the median and the mode when we are not confident that that is the case. Measures of variability within a sample are designed to show you just how spread out scores are. It means something different if scores are widely scattered from high to low, as opposed to when they are tightly clustered around a measure of central tendency. So it tells you something important about differences. There are two basic measures of variability that are typically used. The range is basically just the difference between the highest and lowest scores in a distribution. So it's a very general description of variability. The standard deviation is much more commonly used, especially if you're talking about quantitative data. And what the standard deviation does is it's basically an average degree to which scores are different from the mean in your distribution of scores. So let's say you have everybody at the university takes an exam, some kind of proficiency exam, say in mathematics, and everybody has a score, and the researcher could calculate the average score on that exam. And then they want to know, how spread out are they? Is everybody clustered tightly around the mean, that average score, or are they all spread out all over the place? And is there a way we can describe that variability using just one number? And that's what the standard deviation does. Basically, if you have a low standard deviation or small one, it means that the scores don't vary very much. Most of the participants or subjects in your study are giving a score that's pretty similar. When you have a large standard deviation, that means that you have some people who are way below the mean, some people who are way above the mean, and so on. So the standard deviation is particularly helpful when we're trying to interpret findings, so that we know the degree to which the mean is actually representative of the population. Your authors describe this concept of the frequency distribution, and I've been using that word distribution fairly often in this lecture, so we need to spend some time talking about what we mean by a frequency distribution. Remember how I used the example of, let's say we take all students at the University of Mount Union and give them a math test. So every single individual in that group has a score. We can graph it out into what's called a frequency distribution, and that can give us a visual impression of what that score, that score group of scores for that entire sample, what it looks like. How are they distributed across the range of scores? So basically what a frequency distribution does is it shows you the probability that the results that you're getting are going to be due to random variability. Now that's, your authors kind of take a jump there. So basically we have an ideal image of what a frequency distribution should look like, and it's this perfect bell-shaped curve. Then you collect your actual data. It's not going to be a perfect bell-shaped curve, but we want to know, like if you have two different groups. So let's say at your university you've done a big intervention to try and improve scores on a math exam, and you want to know if you compare students who engaged in that program versus students who did not, and you want to know if they're different. You're going to create frequency distributions for each group and do some comparisons. What the frequency distribution does for us in terms of visual presentation is to organize the data in a way that allows you to determine the frequency of each score. So the most common scores are going to be clustered around the mean, around the center, and then they are typically going to become less common as you move farther and farther away from that mean. Distributions can either be quote-unquote normal, which means that they're a perfect bell-shaped curve with scores tightly clustered around the center and then becoming less and less common as you move away, or they can be skewed distributions, meaning that their shape is not that perfect bell shape that you could fold over in the middle and have both sides look the same. Skewed distributions are not like that. They tend to have one kind of end of the distribution having the more common scores, whereas the other end is a big long tail. And I'll show you some images here in a second. Now this graphic is of a typical normal curve. It's also the same kind of graphic that I'll show in the next slide that comes from your textbook. But basically the main characteristics of a normal distribution, the mean, the median, and the mode are all exactly the same, and you have a symmetrical distribution, meaning that you can fold this picture in half across that dotted line that's down the center of the dark blue. So right here, you could fold it in half and the two sides would overlap perfectly. Now, looking at the graphic from your textbook, there are specific kind of mathematical characteristics to the normal curve. In a normal distribution, as I said before, the mean, median, and mode are all exactly the same because the normal distribution is symmetrical. In addition, in a normal distribution, you're going to have about 68% of the scores are going to fall within one standard deviation of the mean. So on the graphic here, you've got +1, -1, the 1s, 2s, 3s on this graphic, whether they're positive or negative, represent a standardized distance away from the mean, and we refer to that as a standard deviation. So, the bulk of your scores, 68%, are going to be within one standard deviation, and then the farther you get away from that mean, the lower the percentages are going to be for the number of scores. Now, there are some other kinds of normal distributions. They differ in terms of their standard deviation. So both of these images, the teal colored and the green colored distributions, are normal because they're symmetrical, but one has that really typical bell shape, whereas the other is much more squished. That's such a precise term. The scores are much more concentrated, so you have a much lower standard deviation in curve A than you do in curve B, which would have a higher standard deviation. Skewed distributions are asymmetrical, meaning that if you have a skew off to the high scores, it's going to pull your mean in the direction of that tail. So the blue line for the mean, when you have a skew that's to the right, is pulling the mean toward the tail that is stretched out. The median is going to be a little less affected. The mode isn't going to be affected at all because it's the most common score. The mean is affected because it takes into consideration every single score in the distribution. The left skew, again, the blue line, the mean is pulled toward the long tail. The mode stays where the most common score would be, the median somewhat less affected than the mean. So in a right skew, it's also often called a positive skew because it goes toward the high scores. The left skew is often called a negative skew because the skew is in the direction of lower scores. I tend to prefer right and left just because it's less confusing than positive and negative. Statistical significance is one of those complicated constructs that in a course like this, I don't like to spend a great deal of time talking about statistical significance. If you are a major in one of the social science disciplines, you will eventually be taking a research methods and statistics course or a series of courses where you will learn more about statistical significance. But suffice it to say that if we want to determine the degree to which a finding is reliable and theoretically reflective of the way the data actually is. For example, if I have two groups, or go back to the example I gave of my CSI study, where I wanted to know, are my three groups of participants, are their scores different? Are they statistically significantly different from one another? So for example, when I compared my participants who had watched the stigmatizing CSI episode versus those who had watched the non-stigmatizing CSI episode versus those who had watched When Weather Changed History, were their scores on the dangerousness subscale of my measure of stigma? So in other words, how dangerous do you think people with mental illness are? Those who watched the stigmatizing CSI episode had significantly higher dangerousness estimates than those in the non-stigmatizing CSI episode, and those who watched the non-stigmatizing episode had significantly higher dangerousness estimates than those who watched the weather episode. So what I did there was I did an analysis of variance test and ANOVA, as they're called, and the question you're asking there is the size of the difference between the means of those groups, those experimental groups, is it meaningfully, reliably different? And what you're wanting to say is, if I ran this study 100 times, I'm going to find that finding 95% of the time. If I can find it that at that level of significance, then I'm pretty confident that my finding is not accidental. So that's really what we do when we talk about statistical significance. We're making a probability assessment of how likely is it that the findings I see in my study, if I were to repeat it over and over and over, how likely is it that I would get the same finding again? So sometimes people in the public who don't have stats training, when they hear the word significant finding, they often think that means it's a huge finding, like there's a massive difference between groups. That's really not what statistical significance means. What statistical significance refers to is the likelihood that the finding you got today is an accident. And you want to be able to say that there's a less than 5% chance that the finding you found today was accidental. So we try to create greater certainty that what we're finding is meaningful. So that concludes my coverage of Chapter 1.